Hello, everyone. Thanks for coming to my talk, despite the scary title. I'll be speaking about moment polynomial optimization in infinite dimensional spaces. So that's a joint work with Alessandro Rudi, and he's one of the co-organizers. So there is some connection with the workshop, but I will not speak about non-commutative things, and I will try to make connections with optimal transport, even though it will be mostly the motivation at the beginning. And then I'll speak about what the title covers. So let me try to make a connection with what I've seen so far. So many talks started with photographs of Kantorovich. So I'll try to find one which was not shown yet. I think this one was not shown. It is in Prague in '81. And of course, there is no photograph of Gaspard Monge, but in Paris, there are several things that are named to Monge. So there is a Place Monge, there is a Rue Monge, there is even a metro station with his name. And so my background is in control and convex optimization. So for me, optimal transport is just a linear optimization problem. And it seems that actually the Kantorovich formulation of the Monge optimal transport problem is the first documented instance of linear programming. It was in the 40s, and maybe somebody knows earlier instances, then please let me know. But it seems that it's the first LP linear program that was proposed, and interestingly, that was an infinite dimensional one, and that was a convex relaxation of a very hard problem originally proposed by Monge several decades before. So linear optimization, convex relaxation, this is what my talk is about. So that's for me optimal transport. The unknown is the plan pi, and you see that it enters the problem linearly. And for the techniques I'm interested in, I will have polynomial data. And by that, I mean that the integrand, the cost C, and also the test functions P and Q, and also the supports of mu and nu will be described by polynomials. And once we restrict this to be polynomials, we have what Jean-Bernard Lasserre called the generalized problem of moments, because these are constraints on the moments of pi, and the objective function is also a linear function of the moments, and the unknowns are the moments. And over the year, the last 25 years, we have been developing techniques, it's called the moment sum of squares hierarchy, to deal with this generalized problem of moments. That's numerical optimization, but I will tell you more about it. I don't believe that a lot of people are familiar with it. In a nutshell, it's a family of numerically tractable finite dimensional convex relaxations, and typically these are semi-definite optimization problems. And so if you want to have an idea of this idea of generalized moment problem is a reference by Jean-Bernard. I will give more references after. So once we solve this problem of moments, you may want to retrieve the optimal transport if there is one. And for that, we developed more recently a technique based on kernels, Christoffel-Darboux polynomial kernels, which allow to retrieve the transport map, if there is one, from the knowledge of the moments. So this is something we can really do now with convergence guarantees. And here too, I put a few references about these techniques. This is something more recent. And if there is no transport, you still have moments, which can model every transport plan. It doesn't have to be concentrated on the graph, as probably most of you know already. So originally, these techniques, they were not developed for optimal transport. They were developed for a finite dimensional polynomial optimization, which is the problem of minimizing a polynomial, real-valued polynomial, subject to polynomial equations and constraints. So this is a difficult non-convex optimization problem that includes all combinatorial optimization problems. So you can imagine that it's a difficult task. And after that, that was in early 2000, we extended these techniques to deal with infinite dimensional problems. So this includes optimal transport, but many others. Currently, we are working on extensions of these techniques to even more challenging setups, namely non-commutative polynomial optimization, but I will not talk about it, not today, and infinite dimensional polynomials. So polynomials on infinite dimensional vector space, and this is the topic of my talk. So I will be try to extend the existing moment sum of squares hierarchy for polynomial optimization over infinite dimensional spaces, and I try to keep the development as simple as possible. I'm not interested in full generality, but I'm interested in just the extension from finite dimension to infinite dimension, which is the easiest, to me at least, to understand and to explain. Okay, so that was the introductory part on connection to this workshop topics. And now I'll speak about the use of moment sum of squares methods in finite dimensional polynomial optimization. And of course, I have no time to explain that in detail, but hopefully you'll get the main message so that I will be able then, in the third part, to extend this to the infinite dimensional setup. So this is what we call a POP, a polynomial optimization problem. P of x is a given polynomial of the indeterminate x, which is a vector, finite dimensional. Capital X is a domain, so it's described by polynomial equations and polynomial inequalities, which are not displayed here. P star is a value, and we are especially interested in a global minimization. So we don't want local minima, we don't really want bounds, even though we'll produce bounds, but we really want the global minimum. So as I said, this is a challenging problem that includes all combinatorial optimization problems, so you cannot expect this to be solved for arbitrary size, even though we saw during this workshop techniques to exploit symmetry, for example, that would scale respect to the dimension of x. So that's my notation for a polynomial. For convenience, I use monomials. So this is a product of the scalar variables raised to integer powers. And then I sum, that's a finite sum over indices, which is this vector A, bounded by D, the degree, the total degree. And, okay, so these are the polynomial defining the set capital X. The GI are given multivariate polynomial just like as P. This we call a basic semi-algebraic set, and we assume it's compact because it makes our life easier in the sense that since we're minimizing a continuous function on compact set, there will be a minimizer. Otherwise, we can relax compactness assumptions, but it's a little bit more technical. So the data is GIP, and we want to find P star, the value, but also possibly the minimizer, one minimizer. So a value of x such that P of x is equal to P star and x belongs to capital X. Well, if you look at this problem a little bit more, you realize that as soon as you have a nonlinearity here, you can replace it with a linear term. So somehow you write the polynomial as a linear function of the monomials, and then you convexify or relax the monomials in a way that actually they will belong to the convex hull of the set of monomials. And this is nothing but the moments of probability measures on the set of interest. This we call the moment body. And so why does that work? Because here you take the convex hull and you minimize a linear function on the convex hull. So if you minimize the same linear function on a non-convex set without the convex hull, it would just give the same value. Okay, so because of linearity, putting the convex hull operation here does not change the value. So it's not a relaxation. As soon as you're able to describe this moment body, and of course this is where the main difficulty is, explicit characterization of this convex hull is difficult. It's quite difficult to know whether a given vector, finite dimensional, belongs to the set or not. This is the so-called problem of moments, and it has been studied since the 19th century, and that's not an easy problem. Okay, so do you have questions on that? Because this is one of the basic ideas behind this moment sum of squares hierarchy. All clear? That's an example in one variable. You have x here, x squared, and x cubed, and x belongs to this interval. You see, the red curve is this nonlinear three-dimensional vector, x, x squared, x cubed, and the blue guy is a convex hull. So, as I said, this moment problem, truncated moment problem, consists of finding whether a given vector belongs to the moment body. The moment body, as it is difficult to manipulate, and what we do is that we approximate it using objects that are easier to manipulate. And in particular, we'll use semidefinite bodies, which are linear sections of the cone of positive semidefinite matrices or non-negative quadratic forms, because we can optimize over these objects with powerful numerical algorithms, which have been developed since the 90s, late 80s. This is called semidefinite programming. It's a broad generalization of linear programming. And so, since the moment body is not directly semi-definite representable, it's not a linear projection of a linear section of the cone of semi-definite matrices, what we'll do is that we'll approximate it using these objects. And we do it in a principled way, such a way that we'll have a family of outer approximations which will be tighter and tighter. And this can be proved mathematically, and the proof is based on the dual perspective, which I will not present today. And it is results of real algebraic geometry on the representation of polynomials which are positive. These are called positive Stein-Zets. So if you want to know more about this technique, which has been around for 25 years, here are a few recent references. There are no books on that, and also courses. So it's, I would say, rather standard in the optimization literature. And that's a fascinating area with connections to probability theory, real algebraic geometry, and many other domains. So now, that was my quick overview about moment sum of squares in finite dimension. Now I'll try to investigate what can be done in the infinite dimensional case. So how can we make sense of a pop in infinite dimensions? So now X is a vector, but in a Hilbert space. Well, what is a polynomial already? We should address this question. And once we agreed on what is a polynomial in this Hilbert space, can we solve the pop and can we solve the corresponding moment problem, just as we did in a finite dimensional case? So is there anything like infinite dimensional moment sum of squares hierarchy? And our motivation for asking these questions come from these domains, so optimization and control beyond ordinary differential equations. So we are interested in nonlinear stochastic differential equation and nonlinear partial differential equations. This will not be covered today, but that was the main motivation. And so a few years ago, I met Alessandro Rudi, and he's an expert in harmonic analysis, and so he helped me understand more this geometry of infinite dimensional spaces and analysis attached to it, and this is the result of our joint work. So we start with a Hilbert space which is as close as possible to what we have in finite dimension, so separable Hilbert space, and a complete orthonormal system attached to it, and of course a scalar product. And so what we call a monomial will just be products of the variables. They were called x1, x2, x3 in a finite dimensional case. Now they are just scalar product with respect of x, respect to the orthonormal system, and these are real numbers, and we take just integer powers and multiply them. And the sum here is, the product here is finite in the sense that this A is a sequence of integers or rational numbers with finitely many non-zero entries. We do not allow infinite products. This will not be called a polynomial if you have infinite products of powers of linear forms. So that's a monomial, and of course you take convex, linear combination of monomials, and this is how we construct a polynomial. And the PA are real numbers, or complex numbers if you want. These are scalar coefficients, and they are indexed in the support of the polynomial, which is a subset of these sequences rational vectors with finitely many non-zero entries. And now you realize that there are two notions of degree attached to this polynomial. The first notion is the notion we had already in finite dimension. This we call the algebraic degree, just the sum of the indices, the largest sum of the indices arising in the here, the support. But we also have another notion of degree, which we call the harmonic degree, which is the largest value of k that you have here. How far you have to go in terms of these countably many, infinitely many coordinates to define your polynomial. Questions?
So basic question, sorry. If I change the basis, is a monomial still a monomial in a different basis?
If you change the basis, these will be different monomials indeed, yeah. It's a matter of choice. You choose the basis and then you call this monomial, but of course there is many ways to do it. You choose your favorite orthonormal system. Yeah. Other questions? Okay, so we work also on a Hilbert space which is regular enough so that we don't have too much troubles with regularity issues. So Sobolev space, and Sobolev space means that a certain number of derivatives of the function, they are multivariate derivatives, partial derivatives, are L2, are square integrable. So finitely many. This we denote HM, TM. That's a typo, that's Tn here. That's the number of variables of the underlying parametrization. So these are, if you think of, these are copies of the unit torus, so these are angles, there are n of them, and this is the degree of regularity. So this hopefully these are called theta here. This will be a little bit clearer in the next slide. So now suppose we have a measure on some subset of H, maybe the unit ball, with respect to the norm. Then the moment of the measure of index A will be defined as we did before. And you see that each of these guys here are actually scalar products, so they are integrals of the underlying coordinates, the theta. And so that's a particular case. We choose the Sobolev space of functions on the multidimensional torus, and the orthonormal system are complex exponentials. It could be something else, but this is one of the simplest setups you can think of. So if you think of n equals 1, these are Fourier coefficients, and you take polynomials of Fourier coefficients. You multiply these Fourier coefficients, finitely many products. So we have the Fourier coefficients can be understood as moments, they are integrals, quantity. and we have polynomials in these moments. And now, if we have a set of indices, we can define the Sobolev moment cone as a set of numbers, scalars, such that there is a measure whose moments are these numbers. And so we have this infinite dimensional version of the truncated moment problem in Sobolev space, which consists of asking whether a given vector, here it's complex numbers, but that could be real numbers if I start with real basis, may use, I don't know, Chebyshev polynomials, whatever, belongs to this set, to this cone, to this moment cone. I hope this makes sense. Now to address this problem, we'll map the set of functions in this Sobolev space to the set of its Fourier coefficients. For that, we use the Fourier transform. And so instead of being in the space of functions, we'll have sequences, small L2. The joint map is the inverse Fourier transform. And, well, all of that is very classical harmonic analysis. So that the unit ball in the Sobolev space, the set of functions whose norm in the Sobolev space is less than 1, can be mapped through the Fourier map, capital F, to a set which is actually an ellipsoid. So its axes are with weights. The weights are these numbers. And this ellipsoid turns out to be compact with respect to the topology of small L2 sequences. There are many ways to prove that, but one way is to just remark that it is included in the so-called Hilbert cube. So you see, it is just like a finite dimensional cube, but the width of each coordinate shrinks when the degree grows. And this is a compact set. You see, you have these weights, and the higher is the degree, the larger are these denominators. So that we have actually, in the space of Fourier coefficients, a compact set. Now we'll do the same manipulation, but with measures. We take the push-forward measure of the Sobolev measure through the Fourier map. This is the Fourier measure, nu. And so instead of having moments on the unit ball of the Sobolev space, we have moments on Fourier coefficients on this compact ellipsoid. And our Sobolev moment problem can be reformulated as a Fourier moment problem. Now you see you have a moment problem in infinite dimensional variables, these Fourier coefficients. The support is compact. There are countably infinity many variables. And I told you that in the finite dimension, the solution to the moment problem is semidefinite outer approximation of the moment cones. The convergence of it was proven thanks to results of real algebraic geometry and the representation of positive polynomials, positive Sternensätze. If we want to prove convergence of semidefinite approximations of the Fourier moment cone, we'll have to use infinite dimensional positive Sternensätze, invariably. Okay, so that's the punching line of this third part. We started with Sergei and his ball, and we ended with Joseph and the ellipsoid. So again, like the Kantorovich-Monge problem, that's a French-Soviet affair. So approximation results. In complete analogy with the finite dimensional case, the cone of moments in the Fourier domain, in Fourier ellipsoid, will be approximated by linear projections of linear sections of the semidefinite cone. So semidefinite cone is this cone of matrices which have non-negative eigenvalues. They are symmetric, non-negative eigenvalues. It's also the cone equivalently of non-negative quadratic forms. And it's a nice cone that has been studied a lot, as I said. Here is just a representation of 3D rendering. I think it's a 5x5 cone slice, so that the slice is of dimension 3. And you see that it's not a polyhedral cone. It has corners like a polyhedron, but otherwise there are faces which are inflated. So it's a cone on which you can do optimization using the log-det barrier functions, interpoint methods. And this is the realm of semi-definite programming, optimizing linear functions on this guy. And so, as I said, to use this semi-definite cone to have approximation of the Fourier moment cone will rely on positive Shellensets, sum of squares representations. Sum of squares representation of positive polynomials in infinitely many variables. And okay, that's not an easy problem, but people in algebra, in functional analysis, have been studying these positive Shellensets in infinitely many variables. And here are a few references. Jacobi with Prestel in the early 2000s proposed an Archimedean positive Shellensatz for general commutative unity algebra. So this includes polynomials with countably finitely many variables. And more recently, it has been revisited by several people, including Salma Kuhlmann, Marine Fusino, and their co-authors. And so now we are equipped, technically, with these results to prove convergence of our approximations. And the kind of result we can achieve are here. That's my most busy technical slide. So, it's about convergence guarantees, so it's difficult to have it not technical. But in essence, we have a family indexed by 2 degrees, total algebraic and harmonic degree of outer approximations of the Fourier moment cone, which are such that when both degrees go to infinity, up to taking the closure, we have the whole cone. We can estimate the distance between in the Hausdorff metric between the cone and its outer approximation as function of the degree. And even though it's not described here on my slides, but you can check the paper if you're interested. We can also have a family, or we say a hierarchy of inner approximations using measures with sum of squares densities. And the original finite dimensional version of it was also proposed by Jean Bernard some years ago. So we have family of approximations from outside, from inside. I should say, this is not written here, but that they are nested, embedded, these approximations. So the bigger R and rho, the closer I am to the original set. So they are tighter and tighter, outer approximation. And we have the same property for the inner approximation, which I denote C in. And, whoops. Yeah, now we are fully equipped with these results to solve the Sobolev pop formulated in the Fourier domain, equivalently, as a linear program, just as we did in the finite dimensional case. As soon as we are able to describe the moment cone on capital E, this Fourier ellipsoid. So if we replace the Fourier moment cone by its outer, respectively inner approximations, we have a family of respectively lower and upper bounds on the minimum, indexed by what we called the relaxation degrees, R and rho, monotonically, and with convergence guarantees when the degree goes to infinity. Questions? So in the finite dimensional case, we have exactly the same convergence guarantees. The main difference is that we have only a single notion of degree, this algebraic degree. We don't have harmonic degree because there are finitely many coordinates. Okay, a few examples to illustrate this. So they are elementary examples, but hopefully understandable. So I start with this Sobolev pop. So you see I'm in H0, so there are just L2 functions on the torus, one variable, and my harmonic degree for the relaxation will be 1. Yeah, so that's a regularity degree 0, number of variables in capital T. And as I said, so as soon as you have a product of linear functionals, and there are finitely many of them under the product, we have a polynomial. So here I took this example of degree 4, just to illustrate the fact that as soon as we have a linear product, this is nothing but a Fourier coefficient. So it corresponds just to a complex number, or here it's a real number, or I should take conjugation if I wanted to make a complex number. And here I took it at purpose non-convex, so that there are two solutions to this problem. And this is the Fourier ellipsoid here. It's actually a ball because we go only up to harmonic degree 1. And already by truncating to first harmonics, and using the hierarchy, the moment sum of squares hierarchy, we have global convergence of the hierarchy. We can retrieve the Fourier coefficients corresponding to this. Once we have the Fourier coefficients, you do the inverse Fourier transform to get back to the function, which is obviously very simple here, achieving the global minimum. So it's a global minimum because the function is non-negative. So since we have 0, it's necessarily optimal. But we have also a convergence guarantee thanks to the moment sum of squares hierarchy and the so-called flatness condition on moment matrices, which has been mentioned by Jean-Bernard the first day, I think. Okay, a little bit more challenging are what we call the algebraic Sobolev pop, which are linear functionals of a polynomial functions of a function and its derivative. Okay, here's an example. So I have a function on the torus, on the multivariate torus, x of theta, but I also have its derivatives. But as you know, Fourier coefficients of the derivative will be linear function of the Fourier coefficient of the function. The challenge here that even though we have finite algebraic degree polynomials, since we have a nonlinear function of the Fourier coefficients, there will be infinitely many variables. So the harmonic degree of this problem will be infinite. So we have this additional difficulty for this class of what we call algebraic Sobolev pop. Algebraic means that the algebraic degree must be bounded. This is always true, but the harmonic degree doesn't have to be. Okay, so we have a truncation to do. So you see, if you take this example, again, the double well degree 4 polynomial. Here I want to minimize it at 0. So sigma is a direct measure at 0. If you express it into the Fourier coefficient basis, you have these convolutions. So you have infinite sums over rational indices. So it has degree 4, but it has infinitely many variables in this expansion. And so you have to invariably to do computations to truncate it. Here, actually, we also can prove global optimality of the solution at the smallest possible relaxation order. And this implies, actually, that all the higher harmonics are 0, so they can safely be removed. The problem is very, very elementary. And that's it. Thank you for your attention.